finished everything in terms of material. So we're going to do probably for a couple days or whatever we got left there in terms of lecturing and stuff like that is I'm just going to kind of, and hopefully it'll be helpful for you. Just going to kind of go back to the beginning and kind of roll through kind of each chapter, kind of talk about, again, some of the highlights, if you will, or main points of those chapters. And, hopefully it'll be kind of a good review for, the stuff that we obviously covered in those chapters and for the final that's coming up. Again, along the way, obviously, if you have questions on any of this stuff or want to, again, sort of clarify what we're talking about, or you don't remember talking about it in the first place, which I hope is not the case, just feel free, obviously, to, ask a question if you have any questions or anything like that. So I'm just going to kind of, like I said, just kind of go back to the first chapter we started with, which was way back in, I'm not sure what month we started there. I think it was January. And again, we'll just kind of proceed through those chapters, and wherever we kind of leave off today, we'll kind of pick up perhaps on Wednesday or Monday for a little bit. And then obviously maybe on the following Wednesday as well. We'll kind of clean up everything else. Okay, so I guess really the first thing that we talked about here, and obviously was a pretty big topic in this class, was obviously from, I think, chapter 13 there, which obviously it dealt with equilibrium. Yeah, I probably will post these recordings if you want. Yeah. So this is chapter, I think, 13. And obviously that was, as you know by now, the big topic of the season, which was basically equilibrium, right? So we started talking about equilibrium sort of up front. And as we talked about, and obviously as we've seen throughout the semester, obviously equilibrium deals with reversible reactions, right? So a certain type of reaction that we see equilibrium sort of happen. And those, again, are reactions, right, that have those arrows that are heading basically in both directions, right? And again, what we talked about is there's basically a forward direction where basically it's going from reactants to products. And obviously at some point, once we build up enough of those products, we will get that reverse reaction, right, to take place, where some of those products then combine basically and come back the other way. These are typically a lot of things, that you've seen before, kind of like weak electrolytes and stuff like that, but there is a back and forth. And as we talked about many times throughout the semester, when those rates of the forward reaction equals a reverse reaction, that is really what we mean when we say something has reached chemical equilibrium. So when we talk about chemical equilibrium, we're really at that point where the rate of the forward reaction equals that rate of the reverse reaction. And again, that's kind of into kinetics, like what we talked about just in this last chapter, really talking about how fast it's going in one direction will equal how fast it's going in the other direction. And remember that the importance of that is it does not necessarily mean that we end up right with the same amount of everybody on each side. We don't end up with the same numbers in terms of concentrations of reactants and products or anything like that. But what happens when we do reach equilibrium is at that point, pretty much everybody sort of locks into place. So whatever their concentrations may be at that particular point, because the rate of it going back and forth is pretty much equal to each other, there's really not much movement happening on kind of either side of the arrow. They sort of lock into place unless, of course, you do something to kind of screw up that equilibrium. But they will pretty much lock into place. So again, a reminder, it doesn't mean that, at that point, the amount of A, B, C, and D in my little example there would be the exact same numbers on each side. It just means wherever they're at that point, the rate of the forward and reverse reaction will equal each other. They will basically maintain those concentrations or even those pressures if we're dealing with gases, obviously, and not really change unless something happens to sort of mess up that equilibrium. We saw that obviously a very big letter in this class was K, which is the equilibrium constant. And we could write an expression that is a constant value, obviously, for equilibrium reactions. And, if we do it with, in terms of concentrations, we could call it Kc. And Kc would be really our products over our reactants. And here in this example that I had up there, if we were to write the Kc, it would be the concentration of C squared times concentration of D cubed divided by A squared and B. Remember that here, when we're dealing with equilibrium, we do actually use those coefficients. Unlike in pretty much most of kinetics, we don't use them. But here we do use those coefficients as the exponents when we put it into our equilibrium expression. If we're dealing with gases, as we also talked about, you could write sort of an equivalent equilibrium expression. So we'll just assume, for the sake of argument, everybody there was gases. We would do the same thing. Again, it would be the partial pressure. We would still need to square it of C times the partial pressure cubed of D. And that would then be divided by the partial pressure squared of A times the partial pressure of B in this particular case. So we can have a relationship in terms of equilibrium where we look at concentrations. We can have a relationship where we look at pressures. And if you remember way back when we perhaps were talking about, or even in kinetics, and for example, sometimes, it's easier to follow pressures, right? Especially if you're dealing with gases. A lot of times, for example, those things do not have any type of color associated with them, like a lot of solutions do. Remember, when a solution has color, we could kind of follow absorbance values, right? And that's related to the concentration and how it's changing. We could do something like a spectrometer there, right? And sort of follow the change in absorbance, right? Which would be really, absorbance will be proportional to the concentration basically change. And that's when we have, a solution that again gives maybe a red color, a blue color or something like that, where we can really kind of follow those changes. Obviously, if we're dealing with gases, perhaps that's not going to be so easy. So we could follow something like changes in pressure and kind of relate that to sort of the equilibrium. It's important to note that, again, Kc and Kp, as we talked about, in most cases, can occasionally happen, but in most cases, the Kc value and the Kp value usually are not the same numerical value. Again, it can potentially happen, but usually they're not. But they do sort of tell you kind of the same situation. And remember that when we talk about what does that value tell us, we have the equilibrium constant, which basically means if we have a large value, when we reach equilibrium, we would mainly expect to have products present. And again, just mathematically speaking, as we've talked about a number of times, obviously we take a large number divided by a small number, we're going to end up with a large number, which means we should probably have more products at equilibrium than reactants, and vice versa. Obviously, if we have a small number, we would expect more reactants to be there at equilibrium. And again, just mathematically, that would mean we would have perhaps a larger amount of reactants on the bottom. So a small number divided by a large number gives us a small number. Remember that huge, big, giant number when we think about large number is above 1, that really big number of 1. And so again, technically speaking, anything sort of over 1 is considered a relatively large value of K. And we've seen over the semester here sort of extremes in terms of Ks. We've seen ones that are very, very large, like we saw with Kf sort of values. We've seen ones that are very, very small when we were dealing with KSP values, right? Those are very, very small. So there's sort of a big range, if you will, in terms of sort of equilibrium constant values. And remember that, it does sort of dictate sometimes how we sort of do calculations or involving calculations that involve equilibrium, depending on sort of that value of K. Now, remember that in addition to sort of K in this sort of first chapter, we did sort of also see another letter, which was Q, and Q was the reaction quotient. And Q is calculated the exact same way as you calculate K. Again, pretty much the same as you calculate K. And we use Q sort of early on here in a couple of situations, but really mainly we use Q up in this chapter talking about the idea of, whether or not a reaction is actually at equilibrium. So remember that we kind of do this with sort of maybe initial concentrations, and we use this to help us determine, if we are at equilibrium in a kind of traditional Q problem. And if we're not, it will also help us determine which way we need to go to reach equilibrium. And remember, we do that basically by comparing the Q value that we calculate to the K value. So if Q is greater than the K value, that first off tells us we're not at equilibrium. And in order to reach equilibrium, kind of going opposite where that's pointing, you would kind of need to go to the left in the reaction or head towards the reactant. If Q is actually equal to K, that is a situation where we are actually at equilibrium. And lastly, obviously, you could have Q is less than K. Again, this tells us we're not at equilibrium. And again, in order to reach equilibrium, we would need to head to our products. So we saw kind of Q in sort of two situations when we were in this chapter. One was, as I just mentioned, pretty much a problem such as this, where it simply gives you some concentrations. It tells you maybe you're not at equilibrium. We're not sure if we're at equilibrium. These are some initial concentrations. And you would basically just put it into the Q expression and compare it obviously to the K value and determine if you're at equilibrium or not at equilibrium. The second place where we saw sort of using Q, if you remember, was when we actually started doing equilibrium calculations and doing ice tables. And in those situations, we use it when we're given the starting amounts of pretty much everybody in the reaction. Because the only way that you could calculate Q is to take products over reactants, which would imply that you would need at the onset sort of the concentrations of everybody. So remember, there's no possible way you could calculate Q if they only give you reactants. Sort of values and stuff like that. So that's the sort of second situation where we've seen sort of using Q. And again, it's sort of in that place where we would kind of do ice tables really before you do ice tables. So why don't we talk a little bit about sort of, again, those ice tables and all that good stuff when we do equilibrium calculations. Obviously, when we are calculating some type of equilibrium concentrations or even pressures, right? Because remember, we can do these sort of ice tables in molarity. We've done it in moles. We could also do it in pressures. Remember, though, if we do some ice table calculations, pressures do need to be in atmospheres when you're using an ice table. Again, even if they sort of give you the pressures in some other unit and even want the answer in some other unit, you actually have to do the ice table part in atmospheres for everything to come out correctly and do some conversions. So that's an important thing. Remember ice tables. I hope you know about ice tables at this point, but just to make sure, right? Ice tables are initial, our change, and our equilibrium. And obviously, if we had sort of a reaction, we would sort of set it up like so. Just to make up some numbers here. And obviously, in a lot of cases, we're given perhaps just a reactants, so maybe you're told, hey, you have 2 molar of this guy and 3 molar of this guy. And that's pretty much maybe all you're given. Remember, in those situations, if you're just given really the reactants, it's a pretty safe assumption that you could assume that this reaction is heading in this direction towards the products. Also safe to assume you're starting with 0 here. Remember, the really critical part of our ice table is the change part. It does several things for you. Obviously, it determines how things are changing, but it also takes into account the stoichiometry part of it, that multiple relationship, which is why when we do our x's, this is minus 2x, this would be minus x for the coefficients, and on the back end here, plus 3x and plus 4x. And at that point, we would carry everybody down. And obviously, we would go into our equilibrium expression in this case. And clearly, we would start crying because this looks like it's going to be very difficult and stuff like that. But obviously, we won't solve this made up example here. But we do need to sort of solve these guys. Basically, we would then obviously solve for x, which would be our change part in this ice table. Now, what we were talking about just a second ago in terms of Q, in a situation where you are given, again, sort of the starting amounts of everybody, you should calculate Q first when you're going into an ice table. And again, the area where it would potentially affect would be the change part, right? And so, for example, if we calculated Q and it told us we were not at equilibrium, which you probably could guess if you had to do some type of calculation like this, but it needed to go to reactants. What that means is actually the reaction would be heading in that direction, right? So if you did Q, you compared it and it said, hey, you need to make more reactants. What that actually means is our products would be getting smaller and our reactants would be getting larger. So it would affect obviously the signs that we would use in that sort of situation. So that's, again, I would say maybe a little rarer of a case where you might have that situation, but it's always a good idea. Probably 95% of the time, or maybe even more, is probably going to be heading towards the reactant side. I'm sorry, the product side. But again, in that kind of rare situation where you are given, the starting amounts of everybody, you do want to make sure you double check just to make sure, you are sort of heading in the right direction. Any questions on that so far there? Okay, so obviously when we get to sort of this point here, we're solving for it, we really saw sort of, three different approaches where we could kind of solve these equilibrium problems. Obviously, we've had situations where it's sort of like a perfect square on both sides, right? So you can definitely kind of just kind of do that and solve for x relatively easy. We've also seen a situation where it's not such a perfect square, but you end up with your quadratic formula where you need to obviously put it into our quadratic equation here. And remember that when we do this, we do get 2x values, right, using our quadratic. And we've seen over the semester here a variety of sort of answers, if you will, when we kind of solve. You can potentially have, in a lot of cases, a positive x and a negative x. You can also have two positive x's. You could also even have two negative x's. But at some point, one of those x values, as we've seen, will not make sense. So for example, if we got an x value that was negative, clearly if we put it back into here, that would yield us a negative concentration, which we cannot have. So usually one of them will not make sense, or maybe one of them, when you put it back into here, when you do that subtraction, again, will give you a negative number, which you cannot have. So one of those cases, sort of can happen. Remember that sort of the third way that we talked about is you can assume sometimes that x is equal to 0. And remember that we can only do that based on the k value being small. And again, with the idea that the k value is relatively small, what that means is we would mainly have reactants at equilibrium, which means we mainly wouldn't be making a lot of products. And we would assume that the change, which is x, would be relatively small. Remember that when we do that, we can't really get rid of all the x's. It's really just the x's that we're subtracting it from a number or maybe adding it to a number. Those are the guys that typically sort of get taken out of the loop in that case. We do need to always check that because in some cases it's not correct. And remember, we use here in this class what is referred to sometimes as the 5% rule. And basically to check it, you take your x value that you got when you solved it, you divide it by really kind of the initial concentration, which is kind of like the guy you're going to subtract it from, and you times it by 100%. And if it's basically 5% or less, your assumption is good. It's not that big of a difference. Again, if it's over sort of 5%, you do need to go back and solve it some other way. And for us, pretty much that would mean that you would have to default back probably to your quadratic formula. You could, as we've talked about many times as well throughout the semester, if you wanted to, you could just go straight into the quadratic formula and not worry about the assumption. It really should end up the same in terms of your answer and stuff like that. There is sort of a fourth way that we don't really do in this class, but sometimes you will see in books, and sometimes other people will do it. And that's what is known as successive approximation, where you kind of look at a value and go, all right, well, I know the value's got to be less than 3. You kind of put pick a value of 2 or something like that and put it in there and go, okay, and solve for X. And then you kind of keep doing that until the number you put in and the number you take out ends up being the same number. And again, that could take an all-day project if it kind of goes bad for you in that situation. Any questions on sort of the equilibrium ice table type of stuff? Clearly as well, the other nice thing that we talked about in terms of this is that it is really a math type problem, which means when you do solve for your X values and your equilibrium concentrations, you can then put it back into the equilibrium expression, constant expression, and really solve for it. And you should obviously, with rounding, get an equilibrium constant value that is relatively similar to what you had before at the start. Now, we talked a little bit again earlier here about Kp and Kc and some different types of equilibrium constants. And as we've seen throughout the semester, right, even though they got different letters next to them, they're essentially all the same thing. They're essentially all equilibrium constants. It doesn't really matter. But we did see in this sort of first chapter a way to kind of go from Kp to Kc, which sometimes you may need to do. And remember that sort of relationship is that the Kp is equal to the Kc. That's our RT delta N. And this could be a situation where maybe you're interested in the Kc value, but you're given pressures. So you could calculate the Kp up front and then use this to kind of get to the Kc value. Or vice versa, maybe you have all concentrations given to you, equilibrium concentrations, and you're interested in the Kp value. And then obviously you can use this to go from one to the other. Again, this is our equilibrium constant dealing with pressures. This is our equilibrium constant, obviously dealing with concentrations. This is our gas constant, which is actually this guy, not the one with Kelvin or anything like that. That's our temperature in Kelvin. And important as well is the delta N. So the delta N is the moles of the products minus the moles of the reactants. And remember, it's important to not neglect the actual sign that you get with that. So as we talked about, perhaps we have 2A, that's a gas, plus 3B, that's a gas, goes to 4C, that's a gas. When we would do this, we would take our delta N, which would be 4 minus 5, gives us a -1. Again, there's a very big difference in terms of the math and the answer that you would get when you substitute that in for 1 versus -1. Again, the negative means you take the inverse of it or the 1 over it. So again, you want to make sure you just don't kind of just take the difference and go, hey, the difference is 1, because the negative is really important sort of in that situation. Any questions on that one there? Okay, so the other couple of things that we sort of touched upon there in that opening chapter of the season was, sometimes we do need to manipulate equilibrium sort of reactions. And sometimes we may need to reverse the reaction. Sometimes we may need to sort of add equations together and so forth. So a couple of things, remember that if we are taking sort of 2 equations and we're going to basically add them together, try to learn the alphabet there we go. So when we do add these together, again, opposite sides of the arrows will cancel, giving us the overall reaction of A plus B goes to E plus F. remember that although we added the equations here, what happens with our K value is that we actually multiply here, not add. So we want to make sure we actually multiply here and not add them together. So that's a very common thing that we sometimes need to do to get to the equilibrium constant. Sometimes we may have a reaction such as this, and we don't need like A and B on the reactant side. Maybe we need it on the product side. So flipping that equation around or reversing that equation, what that does to the equilibrium constant is you take 1 over the equilibrium constant. And that's because basically in that case, your reactants and your products switch places. So in the original equation, your reactants, products over reactants, and then you flip it around. Basically, you're taking 1 over it and you're flipping the K value. So again, here we don't do a negative, which is a common thing that people do. Go, oh, I flipped it around, I'm going to make it negative. So we do take the inverse of it. A couple other sort of manipulations that we talked about was, again, sometimes you may need to multiply a reversible reaction by a common number. So let's say we need to multiply this entire thing again by 2. We do not multiply the K value in this case. We actually square the K value in this case. And again, that's because if we just kind of look at the equilibrium sort of expression for each of these, again, taking our products over our reactants, when we do it for our second reaction here, it would be C squared and D squared divided by A squared and B squared. So essentially going from here to here in this direction, the equilibrium constant gets squared, which is again is why it's a 2. If we multiplied by 3, we would cube the equilibrium constant, multiply by 4, take it to the 4th power, and so forth. And that obviously means that if we decided to go in the opposite direction, so maybe we don't need 2 of everybody, but we just needed 1 of everybody, so kind of going in this direction, we would divide everything by 2. And again, going in this direction, how that changes is it becomes the square root, basically, of that. So we would take basically the square root of K1 in that case, where we're going sort of in the red direction here. And again, same thing would happen if you were dividing by, say, a common number of 3. You would take the cube root of it and so forth. So those are sort of the 4 kind of major manipulations that we do. And obviously this would be a case where maybe you're given several equilibrium expressions or reactions, and you need to kind of use them kind of like Hess's law to sort of build an overall reaction. And again, you just really want to kind of keep track of sort of what you did to manipulate the equations, and then also how the K values change in accordance with that. Any questions on any of that stuff there? We then sort of, if I'm not mistaken, kind of finished up that chapter talking about our good friend Le Chatelier's principle. And remember, sort of this idea here is we have really a system that's at equilibrium, which again basically means what we've been talking about, that, you know, the rate of the forward reaction equals the rate of the reverse reaction. And then what we do to it is we basically add a stress to it. And what we do when we add the stress is we essentially kind of screw up the equilibrium. It's no longer at equilibrium, but it does want to eventually kind of get itself back to that equilibrium condition. And common stresses involve things like concentration, also involve things like pressure and volume. So if we increase the pressure, we decrease the volume. Those are some ways that we could do that. We could also decrease the pressure, increase the volume. A lot of things are related to gas with that. Also, temperature is another one that we can kind of play with, and adding a catalyst as well. So depending on what you sort of do to it will affect it. In terms of concentration, basically it will, if we add more, it will shift away from whichever side we added it to. So AA is a good way to remember that, add away. And that means if you add more reactants, then it will shift to the product side. If you add more products, it would shift to the reactant side. So remember that, when we're thinking about this sort of situation, we're looking at a beaker and there really is no left side, right side, if you want to think about it that way. But we look at sort of the equation to give us sort of our left side, right side. How do we add stuff? Adding is pretty simple. You just go to the shelf, pick up the bottle and dump it in there. And that's basically going to add it. And again, it would shift to the left or to the right, depending again as to what you added. Removing, on the other hand, concentrations, if we decide to remove, it basically works a little bit different. It will shift away from the side you removed. I'm sorry, shift towards it. There we go. Shift towards it. So when we remove it, it actually does come towards the side that we removed it from. So again here, if we remove a reactant, we would expect equilibrium to shift to the left. If we remove a product, we would also expect it to shift to the right in this case. How do we remove things? So we talked about a couple of common ways that we could remove things from a solution. One, you can't just reach in and grab stuff out, but obviously making it precipitate is a very important sort of way that we could remove something from a sort of equilibrium. Also making water. Why is that important? Well, one thing I didn't touch upon earlier that hopefully you still remember is when we write our K values, we do not include any solids or liquids, right? So by making solids, you're essentially taking that out of the equilibrium and you're basically removing it from sort of the system that's happening. And obviously when you make water, that's something that, as we also talked about, you may not be able to physically sort of see that occur, but that's a very common way, especially with anything that involves hydroxide in the reaction or maybe hydronium or H plus involved in there. So that's a very good way we could kind of do that. When we look at pressure and volume, that is usually in terms of gases. When we talk about pressure and volume, usually do gas in that situation. And when we increase the pressure, the volume will decrease. So really in that smaller volume, what we need is it will shift to the side with the least number of gas molecules. And if we decrease the pressure and increase the volume, it will shift to the side with the more gas molecules. And again, the idea there is sort of the change that's occurring is in this decreasing of the volume as the pressure is going up. So by having less gas molecules, it'll kind of bring the pressure perhaps back down, and vice versa. If the pressure is dropping a lot, we need more gas molecules to sort of bring the pressure back up. And that is obviously reaction dependent as to obviously which side has more or less gas molecules. So it does sort of depend on the equation that you're looking at. Now, the last sort of thing that, or another major thing that affects equilibrium is temperature. And this has to do with, it does work really the same as concentration, which means that if you increase the temperature, it will shift away. And if you decrease the temperature, it will shift towards it. And which way is towards or away from it? Obviously, temperature has to do with whether or not the reaction is endothermic or exothermic, right? So if the reaction is exothermic, we know a couple of things. That means heat and energy is being released. That means our delta H value is negative. That means when we look at the equation, we should see heat as a product in that case. And the opposite is true for endothermic. That means our delta H is positive because heat and energy is being absorbed. And when we look at the reaction or equation, we should think of heat as a reactant in that case. So, very common. I would say they give you sort of the delta H value for the reaction. And again, that's mainly how you kind of can determine whether or not, it's sort of heats on the left-hand side or the right-hand side. The other couple of things that we talked about in terms of the Le Chatelier's principle, which is that a catalyst can be added. Remember, as we talked about at the end there the other day, catalysts are not reactants, they're not products. They're just basically added to speed up a reaction, and they will have really no change on the equilibrium here. Other things that potentially could have no change is like adding a noble gas. They're chemically inert. Also, in this situation, we've seen that you can end up with kind of a no change situation happening. And that's when you look at your reaction and there's actually equal number of moles on both sides. So obviously in that case, there would be no side that has more moles or less moles. And that's, again, a potentially another place where we could have sort of a no change occurring. Any questions on that there? Now, just to finish up here on this sort of equilibrium chapter, a couple of things about K, right? Remember that K is a constant value. And that means as long as the temperature is the same, you can start with whatever amounts of reactants or products. You don't always have to start with the same amount. So remember, for example, in this equation that's on the screen here, if I started in one experiment with, say, 2 molar A and 2 molar B, and then I did the same experiment, but I started with maybe like 1 molar A and 4 molar B or something like that, we would expect that when we would calculate the equilibrium constant for both of those situations, they would end up being the same value. And that's because the equilibrium constant is basically the ratio of products to reactants. And no matter sort of what your starting amount is on that, you could even start with some products as well and some reactants. It doesn't really matter because it will always sort of reach equilibrium with sort of the same proportion of products to reactants, which is why it's a constant value at a particular temperature. It's only right when we change the temperature that the actual value of K will change. So if we change the temperature, the value of K will also change. Now, what do we mean by that? Well, what we mean by that is if we were comparing, say, the K value at 25 degrees Celsius to the K value at, say, 45 degrees Celsius, these two K values would definitely be different. But if you kept the temperature at 45 degrees Celsius and continued to run the experiment with different amounts of reactants and products, and again, kept that temperature at 45 degrees Celsius, all the K values that you get at 45 degrees Celsius, again, should be constant. But they definitely will be a different value than what you had when you ran all those experiments at 25 degrees Celsius. So that's sort of, again, what we mean by that. It doesn't mean that, at 45 degrees Celsius, for example, and you did different experiments, they would have different values of K, but it just means between the two different temperatures, if you change the temperature, you will end up with a different proportion, again, of products and reactants in that particular case. And we would expect different values between the different temperatures, but we should expect sort of the same value within the same temperature range. Any questions on that there? So that, I believe, is pretty much everything we talked about there in the opening chapter. That's good stuff right there. All right. So then let us move on to our next sort of topics that we talked about, which I believe came out of chapter 14, if I'm not mistaken here. So we're doing a little chapter 14 action here. And chapter 14 was acids and bases. So we moved from equilibrium into acid and bases, and we have obviously some general definitions of acids. Remember, basically a straight old generic sort of definition of acid and bases is something that's able to produce H plus in solution. Also remember that when we're dealing with acid and bases, H plus and H3O plus, which is the hydronium ion, are essentially the same thing, right? They both basically mean sort of the acidic part of the solution. A base is really something that can produce hydroxide in solution. And when we talk about this sort of producing these guys, it is the free floating sort of in a solution, the amount of H plus that's floating around, the amount of OH minus that's floating around. Well, that looks like delta OH minus floating around. And, that's what the basic definition there of sort of an acid and a base is. And that was done by Arrhenius. And sort of a more universal definition of an acid or base, or a lot of times what people sort of think about in terms of an acid and base, is the Bronsted-Lowry definition. And in the Bronsted-Lowry definition, an acid is a proton donor, and a base is a proton acceptor. So an acid is pretty much somebody that will give up, and it's important to remember, not just an H, but the H plus. The charge is important. And the consequence of sort of the Bronsted-Lowry definition is it does give us some relationships that occur. So if we look at like an acid and a base, we actually get some partners on the other side, which are the conjugate acid and the conjugate base. And what is sort of the relationship between these things? So as we've seen, when we have the acid on the left-hand side, its partner on the other side is the conjugate base. And when we have the base over here, its partner is the conjugate acid. And what makes up sort of the relationship between those two is really the definition of the Bronsted-Lowry, which is this guy is going to basically throw over an H plus. And that means that in order for these guys to be pairs, and the only difference that we can have between these guys is one H plus. So in order for those guys to be pairs, the only difference between them must be one H plus. So because the acid is donating the H plus, it will end up with one less H plus between the acid and the conjugate base. And because the base is accepting the H plus, it will end up with one more H plus as you go between them. So remember that, that is really the only difference that you can have when you're trying to determine if these guys are pairs, are they related to each other. It does has to be basically one H plus sort of difference. Also important is to understand this relationship, because remember, in a lot of questions, you're giving something like, hey, give the conjugate base for like HS minus. And they may not tell you what something is. So a good way to remember or sort of figure it out is to just think about it backwards. So if I'm looking for the conjugate base, that means that what I am originally starting with is an acid. An acid means it should give away the H plus. And then you have a pretty good understanding of what it should be. It should give away that H plus. When we lose the H, obviously we lose the H. But when we lose the plus, we become one more negative, which is how we get to our -2. And that would be different than if it asked for the conjugate acid. Again, if you weren't sure in this particular case, you can use, again, that relationship to kind of work yourself backwards and figure it out. So in this case, if we're looking for the conjugate acid, our partner on the other side is the base. The base is something that will accept an H plus, which tells us that we should, in this case, put the H plus on to get to our conjugate acid. This also brings up a good point, right? Remember, there are certain things that can act as an acid or base, and these guys are what are referred to as being amphoteric. So an amphoteric substance is a substance that basically can act as an acid or base. A lot of times something with a hydrogen and kind of a negative charge has the ability to do that. Water also has obviously the ability to do that as well. Remember that when we talk about diprotic acids, triprotic acids, and stuff like that, things that have multiple hydrogens that could come off, like H2SO4, that these guys actually do come off one at a time. So this sort of stepwise dissociation occurs as they come off. And this is why we talk about the relationship sort of between these guys as being just one H plus, because when we look at this guy, the relationship is these two guys are related to each other. That's just a difference of one H plus. This guy here and this guy here, again, are related to each other by that difference of one H plus. And remember, though, if we try to go from here to here, not good, because that is two H pluses. So although they are technically sort of related to each other, they are not related to each other in terms of Bronsted-Lowry acid and base. Any questions on that there? Okay, so we talked about sort of identifying Bronsted-Lowry acid and bases, obviously being able to write the conjugate acid, the conjugate base, and identifying those things. We then moved into sort of talking about sort of solutions and whether or not solutions are sort of acidic, basic, or neutral. And the first major thing that we talked about was the idea of really when water sort of reacts with water. It does set up an equilibrium. It produces H plus and OH minus. And this gave us our Kw expression, which is the concentration of H plus times the concentration of OH minus is equal to 1 times 10 to the minus 14. So really the H plus, right, is the acid part of the solution. The OH minus is the base part of the solution. We could rearrange this, and it's really the same calculation regardless of which one you're doing. You're basically taking 1 times 10 to the minus 14 and divided by the other concentration. So you could do pretty much the identical calculation on both sides there. Remember that we definitely want to make sure we are using our exponent buttons, definitely in this chapter as well. Otherwise, we will be off when you're doing calculations. But we can compare those two concentrations. If the H plus concentration is larger than the OH minus concentration, that basically means the acid part is bigger than the base part. It's going to be acidic. If the H plus concentration equals the OH minus concentration, that is going to be neutral. And that means that both of those guys at that point would have a value of 1 times 10 to the minus 7 molar. And if the H plus concentration is less than the OH minus concentration, that means that this solution is going to be basic. Really, the basic part is larger than the acidic part in this particular case. Remember that there is a relationship between those concentrations. So, as the H plus concentration increases, the OH minus concentration decrease. So sort of an opposite relationship. As one goes up, the other goes down. So again, obviously, as the H plus would go down, the OH minus would go up in that particular case. Any questions on that there? That led us into sort of a conversation, obviously, about the pH scale. And remember that the pH scale is a scale most people think about in terms of, is the solution acidic? And the pH scale does run from 0 to 7 to 14. Below 7 to 0 is acidic. Above 7 to 14 is basic. And right on 7 really is neutral. And it's neutral because really of this right here. That means that those guys would equal each other, and they both would have a value of 1 times 10 to the minus 7, which would give you, as we know, a pH of 7 in this particular case. As you go from 7 towards 14, you are getting more basic in that case. And if you go from 7 to 0, you are getting more acidic in this particular case as well. Also a reminder as well, before we move away from sort of KW over here, we don't come across it probably too much, but just a reminder that this is a equilibrium constant expression, which means it also is really based on temperature. And usually when we quote this number, and it's usually the number that's used most of the time, that's really for 25 degrees Celsius. So, in a rare instance, that you maybe are not at 25 degrees Celsius, technically speaking, your KW value could actually be a different value. And again, probably wouldn't happen in most cases, but again, a good reminder that, KW is also still an equilibrium, a constant expression, which means if you're not sort of under those normal conditions, you're at some extreme temperature or different temperature, not even really extreme, the actual value of KW could change. Just keep that in mind. Although we don't really think about it a lot, it can also happen, obviously, with our KW because it's nothing more than an equilibrium expression as well. To calculate our pH, we hopefully know that the pH is equal to minus the log of the H plus concentration. And remember that you could also use H3O plus, which is the same thing. If you have a display calculator, that's minus the log, and obviously put your concentration in the proper way with your scientific notation. There's also a similar scale to that, which is the pOH scale, and that measures the minus the log of the OH minus concentration. They both basically tell you what you need to calculate that. And there's a nice relationship between those that we talked about, where if you take the pH plus the pOH, you will end up with 14. It is really, really important, and it sometimes happens a lot, to remember that actually the pOH scale is opposite of the pH scale. So what do I mean by that? I mean that if you are below 7 on the pOH scale, it's basic. If you're above 7, it's acidic. And this is neutral. This is why we talked about a number of times when we're trying to determine whether or not a solution is acidic, basic, or neutral, we should always look at the pH, because that is really the scale that most people have in their head. As you can see, the pOH scale runs opposite of that. So you want to always look at the pH value when trying to determine is it acidic, basic, or neutral. You should really never look at the pOH scale unless you really do understand what you're doing, which hopefully you do. So you could if you wanted to, but most of the time, again, people have that pH sort of scale in their head. And this is situations where it is a very common mistake, when people are answering questions, well, they'll go, oh, I got a pH value of, 10. And a pOH value, I guess that would be 4 in that case, right? And they'll go, oh, this guy is above 7, so it's basic. And they'll go, oh, this guy's below 7, it's acidic. And say the same solution is both basic and acidic at the same time. So sometimes it's a very common sort of error that people make. They sort of give multiple answers for that question. And remember, I think I probably stated it as well when we went through it, that, when you are asked that question, it's all about really one answer. It should either be acidic or basic or really neutral, I guess, in that case. You shouldn't have the same solution being all three. I haven't really ever seen somebody give all three. I've seen people do basic and acidic at the same time. So keep that in mind. And lastly, sort of the other things that sort of finish up some of this type of calculations was if we do have the pH value given to us, we could actually get the H plus concentration from that. And the H plus concentration would be the inverse log of the minus pH. And on most people's calculators, when you do that inverse log, that's a 10 and a caret and a minus pH. And also from the pOH, you can get the OH minus concentration, pretty much the identical calculation, the inverse log of the minus pOH. And again, that would put a 10 and a caret minus pOH up there as well. So as we talked about, this does give you a few different sort of options in terms of how you could solve these problems. As we've seen, you maybe sometimes can solve it using KW. You may also not even need to use KW to solve some of these problems. You could just use sort of the inverse log of the minus pH or POH. So depending on the information given to you, sometimes you have a variety of ways you could sort of solve these problems involving acids and bases. Any questions on that stuff so far? So this led us into obviously calculating pH and so forth for different sort of solutions. And remember, if we're calculating the pH for a strong acid, our base, strong base, really because they're strong acids and strong bases, they're strong electrolytes, which means they will 100% break apart, right? So if we had something like hydrochloric acid, we would expect it to 100% break apart into H plus and say Cl minus. And, if we knew that this guy's concentration was 0.025 molar, it is a 1-to-1 relationship between really the H plus, which is what we're interested in. And we would know that this would also have a concentration of 0.025, which means that's really all we would need to go into our pH equation. So we could go really directly kind of into that equation. Same thing with a sort of strong base, if you had, say, something like calcium hydroxide, right? And if this was a strong base, it also would 100% break apart into calcium plus a couple of hydroxides in this case. And in this case, we don't have H plus, but we do have OH minus. So we would want to kind of find the concentration of OH minus. The difference, though, is here in this case, it didn't break apart into a 1-to-1 relationship. It did break apart into a 1-to-2 relationship. So how that affects concentration is, again, you multiply the concentration by 2, basically. Which, again, I'll do it without the help of a calculator and hope for the best. That will give us our 0.05. Important to remember that this is, again, a base, which means we can go into our POH. So we get our POH in this case, then we obviously would need to get our pH by taking 14 minus our POH in this case to get there. So, strong acids, strong bases are not too terrible to sort of get into and go through. We just want to get the H plus or OH minus concentration. Now, when we delve into weak acids or weak bases, it is a little bit different in that situation. And in that situation, it does require, obviously, ice tables when we're dealing with a weak acid or a weak base. And this is because they're basically weak electrolytes, which means they basically will set up an equilibrium, right? So what happens is, for example, if we look at something like acetic acid, which is a weak acid, when it breaks apart in solution, it breaks apart kind of like normal, H plus and acetate. We could write a Ka expression for this, A being weak acid, and that would be our concentration of our products over our reactants. And again, we would do an ice table like normal. We would solve for X. X in this case would equal the H plus concentration, which would then allow you to go into your pH equation. Again, we would solve these the same way as we know we've solved other equilibrium problems. So if it's a small value of K, you could try the assumption. If it's not, then you could also quadratic it and happen to get a perfect square. It doesn't happen too much with these, I don't think, but you can kind of solve it the same way. Remember that the relationship is as the Ka value increases, the strength of the weak acid also increases. And that's basically the same idea as we have a larger value of K. Larger value of K means that we would have more products. More products means we would have more free H plus. More free H plus means it's a stronger weak acid. Remember, we're talking about a strong weak acid as compared to a strong acid would definitely be much stronger. So something like HCl would be much stronger of an acid than acetic acid, because once HCl goes for a swim, it's going to break apart 100% into H plus, produce a lot of H pluses really quickly, and be considered a pretty strong acid. Acetic acid is going to set up this equilibrium, and because of that, not going to release as much H plus. So it's going to be obviously a weaker acid in that particular case. Also, why we don't see Ka values for strong acids are Kb values for strong bases. Strong acids 100% break apart, which means there's no going back the other way. There's no equilibrium being set up. So we don't have basically a K value associated with it. We also can have the same thing for bases. So when we have weak bases, for example, if we take something like NH3, which is a weak base, plus some water, it's going to actually accept the H plus. Make NH4 plus and OH minus. This is going to give us a Kb expression, again, B for base. And again, we pretty much will do the same thing. We'll do our ice table here. We will solve for X. X, though, in this case, actually will equal the hydroxide concentration, which means you got to first do your POH first and then to your pH in that particular case. So really solve the same way. Again, as the Kb value increases, just like the Ka value, we have kind of a stronger, again, weak base, nowhere near as strong as something like, say, calcium hydroxide, potassium hydroxide, sodium hydroxide, which are really strong bases and basically will 100% break apart and produce a lot of OH minus. Any questions on that there? Also, an important aspect that we talked about in this class is the idea of, when should I be using a Ka value? When should I be using a Kb value? And again, writing the equations correctly can help you with that. Remember that if you write the equation and you look on this side and you see H plus, that should be a Ka situation. If you look on this side of the equation and you see OH minus present, that should tell you should be using a Kb expression. So again, as we've talked about many times this semester, writing these equations are really helpful because it could help you understand what you should be using in these sort of calculations. And we know that there is a relationship between those two things. And the relationship between those two things is that Kw is equal to the Ka times the Kb. So again, that Kw, which again is our 1 times 10 to the minus 14, is a way that we can easily kind of convert from the Ka value to the Kb value relatively quickly. Now, we also talked about with weak acids and the idea of what is known as percent ionization. And that basically is the amount of kind of H plus that comes off in a weak acid, or OH minus in the base. We take the concentration of H plus at equilibrium divided by the initial concentration of our acid, and we times it by 100%. So that is, again, our initial concentration of our acid. That's sort of the H plus concentration at equilibrium. And that'll give us our percent ionization. This is essentially, as we've talked about, how we do our checks, right? We take our X value divided by our initial concentration, and that gives us our checks in that case. So this is another thing. Obviously, if something has a very high percent ionization, it means it breaks apart a lot. And if we have a low percent ionization, it doesn't break apart as much. Concentration, as we talked about, plays a key role in that. If you have a very high initial concentration, just mathematically speaking, when you do this division, you'll get a smaller number. If you have a smaller initial concentration of your acid, you will get a larger percent ionization. I think that was the pizza example I used probably back then. If you have a whole pizza and somebody takes one piece, not a big deal, not so much is lost. But if you sort of have only 2 pieces of pizza left and somebody takes that same one piece, it's a bigger percentage of loss there, right? And that's sort of what we see here with concentration. The bigger the concentration we start with, the little bit of H plus that comes off is not going to be as much of it, obviously, as then if we had a very small sort of part. Now, this here leads us into another really big topic, which was salts, right? And hydrolysis. And there are different types of salts that are produced, and really a salt's produced from an acid plus a base, right? Makes a salt and water. And where salts come from really determine whether or not they will kind of do anything, right? And there's that opposite relationship. If you remember, if something is a strong acid or base, its sort of partner, its conjugate partner, will be weak. And vice versa, if something is a weak acid or base, its conjugate partner, its conjugate acid or conjugate base, will be relatively strong. So we can have neutral salts, you know, like sodium chloride, which most likely came from sodium hydroxide and hydrochloric acid. These are both strong acids and bases, which means this guy would be neutral, and we would expect a pH of 7 in that case because of that. So really anything from group 1 on the periodic table, group 2 on the periodic table, anything that comes from a strong acid is considered a neutral salt, and you could assume that the pH would be 7. Now, if we had a basic salt, like say NaF, that is because NaF most likely came from sodium hydroxide and hydrofluoric acid. That hydrofluoric acid is a weak acid, which means the F minus is going to be relatively strong. So when it's relatively strong, what do we mean? We mean that it will continue on and react with water. And because it came from a weak acid, it will react as a base and accept the H plus and make HF and OH minus. Right off the bat, as we talked about, a couple of things we know without even doing the calculation here, we should know it should be basic. And we also should probably know we should be using a KB value. We would do a nice table here, right? We would solve for X. X would equal the hydroxide concentration. That would get you to your POH and then get you to your pH in this case, which again should be basic in this case. The last type of salt that we talked about here, I know we're a little bit over, just kind of finished this little chapter here, and then we'll continue on to lab, is a acidic salt. And an acidic salt, for example, like NH4 plus. NH4 plus, or actually you want to do NH4Cl, that most likely came from NH3 and HCl. HCl being a strong acid, which means the Cl part not important. This guy being a weak base means that the NH4 plus will be relatively strong in that sense. Again, strong that it will go through that hydrolysis reaction. Since it came from a weak base, it will act as an acid, which is H plus, and that will yield us NH3 plus H3O plus. Again, just like the previous one, we know that this guy should be acidic at this point. Also, probably should be using a Ka value as well. We would obviously do a nice table here. We would solve for X. X would equal, in this case, the H plus concentration, which means you could go right into your pH at that point. Also remember that sometimes an acidic salt can be a small, highly charged positive metal, right? Like, you know, an aluminum sort of cation, right? Can kind of do that with some water attached, you know. So draw it like that. And again, that guy can go through there and kind of produce H3O plus as well. Any questions on salts there? And the last thing that we talked about here in this chapter was another definition of acids and bases was a Lewis acid and a Lewis base. And remember that a Lewis acid is actually something that will accept a pair of electrons. These are usually electron deficient guys, kind of things with positive charges, incomplete octets, guys that are missing sort of electrons make really good Lewis acids. And Lewis bases, we've seen a lot. These are guys that will donate a pair of electrons. And these are guys that actually have kind of more electrons or have gained electrons, things with negative charges like Cl minus, things that have non-bonding electrons and are polar, like ammonia, like water. And sort of the Lewis acid and base definition even allows us to relate things to acid and bases that don't actually even involve hydrogen, like it does with Bronsted-Lowry. So Bronsted-Lowry is pretty universal, but it does require obviously an H plus being transferred and accepted. Using a Lewis acid base definition, we could actually look at this process in terms of acid and bases without even having to actually have an H plus being sort of transferred. Place where we saw Lewis acid and bases a lot was with complex ions, coordination compounds as well, and complex ions really specifically. We think of those sort of interactions again more as a Lewis acid base interaction that's happening as those ligands again are coming in and donating those electron pairs to everybody. Any questions on that? That is chapter 14. So we'll lay it up there for our